Hi everyone, my name is Yaohui Chen. I recently graduated from Northeastern University, advised by Professor Long Lu. I'm now working at Facebook as a research scientist. Today I will present Savior, towards bug-driven hybrid testing. This is a joint work with Peng Li, Sheng Jianguo, Rundong Zhou, Yulong Zhang, and Tao Wei from Baidu USA, and Professor Jun Xu from Stevens Institute of Technology. Fuzz testing has been the de facto software testing technique widely used in both industry and academia. It features cheap resource consumption per execution, and the trade-off is that it does not know much about the program under test. On the other side of the spectrum is symbolic execution. It features sophisticated analysis about the program under test, but with the trade-off of much larger resource consumption. Recent years, researchers explored the smart combination of both, which we call hybrid testing. In hybrid testing, we use fuzzing to explore those easy-to-reach code blocks most of the time. And when it stops making progress, we switch to concolic execution to help unblock fuzzer by solving those difficult branch conditions such as the long magic number comparisons. The state-of-the-art hybrid testing systems are co-coverage driven. Each co-coverage entity could be viewed as a line, block, branch coverage, etc. We denote each entity as a node. And in the example on the right, if the fuzzer finds a new node using the mutated inputs, it will save the input for future exploration. And when the fuzzer gets stuck, we use concolic execution to revisit the same path and find that if there is an extra node that could be reached when the branch condition is satisfied, the concolic execution engine can then call SMT solver to generate a new input that can cover the new branch. The recent hybrid testing systems are all coverage driven. However, we need to be careful as it could be a pitfall that can prevent us from finding those precious bugs, which is our ultimate goal, if we only pursue co-coverage. First, co-coverage alone likely makes bugs. Take the example of this integer overflow from object dump. The bug is in the highlighted code, and we can see that it is trivial to cover this line of code, and the fuzzer won't bother to keep mutated inputs as it won't see any new co-coverage. However, since the section size is controlled by user, if and only if the size is exactly a certain number, we can trigger the integer overflow, and this leads to the allocation of a smaller buffer that could later lead to out-of-bound memory access. The second problem with co-coverage is that it results in suboptimal resource distribution. Taking a quote from the book Code-Complete by Steve McConnell, in 1993, the industry average bug-to-code ratios is between 1.5 to 5%, and in places like Microsoft, with better code quality control and advanced testing techniques, the ratio is only 0.05%. But under code coverage guidance, the fuzzer will treat each line of code equally with the same computation and storage resource. That is, with a very naive calculation, if we are testing the released Microsoft product, over 99.9% of our resource will be spent on places that won't produce any bug if we only rely on code coverage. In this work, we present Savior. Savior aims to tackle these two problems head-on. First, we steer the fuzzer to paths that could reach more potential bugs. And second, when we can reach those likely buggy locations, we can model the bug triggering conditions and then actively solve those conditions with symbolic execution. Here is an overview of the whole Savior system. It includes the compile time analysis and instrumentation of the target program, and runtime components including the fuzzer, the concolic executor, and a coordinator that helps schedule the runs between fuzzing and concolic execution. Next, let's see how the compile time components work. Given a program, Savior first instruments the program with different kinds of software sanitizers. It could be agile sanitizers, memory sanitizers, or undefined behavior sanitizers. Savier's design is agnostic to different sanitizers. It then constructs an inter-procedural control flow graph. With the control flow graph, it computes the number of reachable instrumentations from each basic block and inserts that number at the locations of each basic block. Again, using the object dump program as the example, for the highlighted bug, the sanitizers will mark it as a potential buggy location and instrument the reachable bug number for each basic block as highlighted in the intermediate representation. Next, let's see how the runtime coordinates to uncover bugs more efficiently. With the reachable bug number information, when the coordinator goes over seeds in the corpus of the fuzzer to decide which seed to explore next, it will prioritize the bug number over the code block number. In this example, it favors the third input as it has the most potential to reach more sanitizer instrumentations. After reaching a sanitizer instrumentation, how can we trigger the bug directly? Well, Savior relies on active property checking. It models the common bugs as SMT constraints, and as shown in the table on the right, with this constraint combining with the path constraint, it can ask SMT solvers to directly generate an input that can reach the same sanitizer instrumentation and then further trigger the bug. We also adopt advanced scheduling by combining the static information with runtime statistics. Say, although an input can reach more instrumentations as calculated at the compile time, but during runtime, we know that in the past, the solver has said 99% of the instrumentations are not satisfiable. We will then deprioritize this input in the future. And other interesting tricks like how do we create sound vulnerability labeling to filter those impossible bugs at compile time. Also, we introduced fork server mode for concolic execution to accelerate the CLI execution during runtime. Please check our paper for more details. Next, in our evaluation, we aim to answer these research questions. How is Savier's bug finding efficiency and its code coverage compared with other code coverage-driven testing techniques? We use two benchmarks for evaluation, including LLaVAR-M benchmark and a real-world benchmark programs commonly used in other fuzzers evaluation. We also compare Savior with a bunch of recent advancements in software testing, including AFL as the baseline and AFL Go as the representative of directive fuzzing, and Angora as a fuzzer boosted by gradient descent searching techniques, and two recent hybrid testing frameworks like Driller and QSIM. The figure showed the respective performance of different fuzzers in Lava. In this evaluation, as Lava is composed with smaller size programs, it is easy to cover codes with Lava bugs, but with active property checking, Xavier is able to trigger the most bugs, including many unlisted ones. In the end, Xavier found 2 times more Lava bugs than other hybrid testing tools. Next, let's move on to the real-world benchmark. First, we want to test if sanitizer instrumentation conforms with the bug-to-code ratios we showed earlier. As this table shows, on average, only 12.25% of the code are marked with high bug potential, and hence we would like to think that it is a good proxy for estimating bugs. And it's the same analogy as to the code coverage. You need to reach the code first to uncover a bug, and similarly, you need to perform an arithmetic operations first to trigger an integer overflow. And in this evaluation, as our current implementation of model checking only supports the undefined behavior bugs right now, and we apply UBSend to all the programs we tested for all the fuzzers. And this table shows the number of the triggered violations in total by each one of the fuzzers. And it's worth noting that many UBSend violations are actually benign, and a large number of them do not require fixes after we communicate with the developers. And eventually, after manual triage and communicating with the developers, we found that Xavier in total triggers 481 UBSend bugs, and 243 of them are true positives, including 102 out-of-bound violations and 141 logic bugs. And about half of those bugs are false positives. Examples like using integer as a child array for storage in libjpeg, or the overflow integer expires immediately. A lot of cases like that in libxml. And very commonly, the programs will often have some checks for overflow after it happens. So in total, among those 243 true positives, we confirmed that at least 25 of them are exploitable, and so far 16 of them have been acknowledged by the developers. Next, we would like to evaluate the relationship between code coverage and the capability of triggering bugs. And we can further testify our hypothesis whether Xavier's bug-driven principle could help find more bugs and in a more efficient way. And in the following figures, we present both the bug number and basic block coverage numbers for each programs, and we compare their pattern. It is not hard to say that, in general, tools with good code coverage tend to uncover more bugs. This has been proven in the past. But I would like to direct your attention to these figures, where Xavier does not find the most basic blocks, but it end up finding more bugs. Similar pattern could be found in the other 4 programs, where Xavier did not find many more code blocks than other fuzzers, but it ended up finding the most bugs. And based on these results, where Xavier found 44.3% more bugs on average than the second best tools in 24 hours. However, we can see that its code coverage is not much better than other testing tools. So, to conclude, we observed that code coverage alone is not efficient in finding bugs. Specifically, it results in these two problems. First, it creates a suboptimal resource distribution, and because it's treating each line of code equally. The second problem is that even when a location is covered, if we are only focusing on code coverage, we could still miss bugs in those covered code. And second, Xavier redistributes more resource to those high bug and code ratio locations by directing code coverage further to, instead of reaching more code blocks, now to reach more sanitized instrumentations. And then Xavier uses active property checking to directly solve those bug triggering conditions after we are able to reach those instrumentations. And lastly, Xavier is open sourced at the following link. Please check it out and give us feedbacks. And thank you for your attention, and I will welcome any questions you have.